So I'm really Professor Jari Nurmi from Tampere University, Finland, and I will chair this workshop together with my Italian colleague Salvatore Pontarelli from the Sapienza University of Rome. And if we think about the software-defined networking, so that has separated the control plane and data plane, or forwarding plane, as it's also called, from each other. And there are some immediate benefits from that. So, for instance, it allows control of the network to be programmable because it was decoupled from the forwarding devices. And the traffic could then be adjusted dynamically. The network could be managed in a centralized way, and the underlying infrastructure was abstracted for the applications and services running on it. But that's about the control point of view. Then programmable data plane is the next logical step, and that's the topic of today's workshop. So programmability there allows the forwarding devices to be flexible and implement functionality that is beyond processing just a set of network protocols that were fixed at the design time. And the data plane can be programmed instead of making new hardware version each time when the set of protocols is changing. And this way, programmable data plane can take care of several network functionalities such as load balancing, query processing and caching, network telemetry, and also protocol offloading. And in this workshop, we will take a look at different approaches to design and exploit the programmable data plane. So there are programmable pipelines and packet processors for ASIC and FPGA implementation, where the pipelines implemented on ASIC represent the high end regarding the performance. And that end is represented by Robert Vikander from Packet Architects Sweden, and he will also address the important issue of high-level language entry for the design of high-performance switching and routing chips. But regarding languages, most of us have heard of the P4 language, and today Marco Savi from the University of Milan Bicocca, Italy, has made use of the P4 language for detecting distributed denial of service attacks in the network by estimating the traffic entropy. And the interesting point in his approach is the avoidance of TCAMs, ternary content addressable memories, that tend to be a pain in the ass if you want to have an efficient implementation. And then with the rise of programmable data plane, the network interface cards have evolved to SmartNICs. And SmartNICs boost server performance in the cloud and private data centers through offloading networking-related processing workloads from the servers, CPUs, to the network. And the SmartNICs are typically FPGA-based, and today we will hear from Cheng-Chen Hu, who's with Xilinx Singapore, about their open source SmartNIC approach and its deployment. And programmable pipelines were already mentioned, but how they compare with processor-like run-to-completion architectures, and the different architectural approaches will be compared today by Esam Solfagari from Tampere University, Finland. And towards the end of the workshop, the focus will switch more to services and applications, and as mentioned, network telemetry is one of the services supported by programmable data plane. And if you think about that in-band telemetry, it adds telemetry measurements to the data packets, which is good from the point of view that it enables a wide range of applications that can make use of such information, such as troubleshooting, congestion control, and path tracing. But the drawback is that additional information adds overhead that will degrade the network performance. And Gianni Antichi from Queen Mary University of London, UK, addresses this issue by introducing an extremely low overhead method for in-band telemetry. One of the platforms for developing services for programmable data plane is eBPF, Extended Berkeley Packet Filter, and it's part of the Linux kernel. And eBPF has the drawback that complex network services are difficult to make using it, although it allows creating multiple change services. And Fulvio Risto from Politecnico di Torino will describe a more easy and flexible service chaining mechanism and other improvements developed to circumvent the shortcomings of eBPF. Then in-network computing has been one of the promises of programmable data plane to enable that is enabled by the programmable data plane, and it's using distributed computing paradigm to apply computations on the data on the move. And today, Albert Lerner from the University of Freiburg, Switzerland, argues that programmable data planes can be used as accelerators for data-centric applications, and he will introduce us to challenges and opportunities in making that happen. And at the end of the workshop, we will have a high-caliber keynote given by Nick McKeown from Stanford University and the company Barefoot. This talk is mysteriously entitled "When Networks Are Programmable Top-Down and End-to-End, What Then?" So I'm looking forward to hear his vision on the foreseeable future in programmable networks. But now it's time to move to the interesting presentations in this workshop, and we would like the speakers to keep strictly the timing, as we only have 20-minute slot for each of you, and hopefully there will be also space for a question or two after the presentation. So let me introduce the first speaker. So Robert Vikander is the CTO and founder of Packet Architects, a company which builds switching and routing IPs for ASICs and FPGAs. And before founding Packet Architects, he was the chief architect of Realtek Semiconductor's Ethernet switch product portfolio. And before that, he was the chief architect of SwitchCore, which is a startup in the Ethernet switch chip space, and built the world's first 16-port GE switch router chipset. And Robert holds Master of Science in Computer Engineering from Luleå Technical University. So Robert, the stage is yours as soon as I will be able to stop sharing my screen.
Thank you. Let me start this. Okay. I assume you can hear me.
Yes.
And you can see. Excellent. So we have a. Okay, so I'll introduce Packet Architects. I know that's not this. You don't care about that much, but it gives you an overview of what we do. I'll then talk a little bit about a shared memory Ethernet switch, which you all are using at some point in time. Then we'll move on to our requirements that we had, and then we'll talk about the language that we defined, Packet Architect CPAC, which is a high-level synthesis language, and what we do with it, etc., and how it works. Okay, so we are an IP company. So we develop the IP that's used by vendors when they want to build an Ethernet switch, etc. We're HQ in Lund, Sweden. We've developed Ethernet switching for the last 20 years. Okay, so just so that you have an understanding where I'm coming from, I'll do some introductions. So a customer comes to us, they want to build a chip. The chip consists of a number of SerDes, MACs, PCI Express to send packets to and from the CPU, and then they come to us to the switching core inside that. So that's a typical Ethernet switch from Broadcom, Marvell, or somebody else. So the Ethernet switch itself has an on-chip memory, on-chip buffers, on-chip tables, which is pretty normal today. Or some customers want to do an FPGA, then they have the SerDes, of course, on the chip edge, and then they, in the FPGA array, they then implement our switch routing core. So they basically get source code from us to run through the tools. Okay. So inside that IP then, how does that work? So I'll give you an introduction of how that looks like. First, the data comes from MACs. MACs you can get from pretty much anyone, from many vendors around the world. MACs have different speeds, so then they have the interfaces, different widths, number of bits, etc. That we take into a parameter-sized configuration file. Well, that data goes to the serial to parallel block, which builds what we call cells. What is a cell, you might wonder? Well, a cell is a fixed length of a packet, of course. And you then determine the cell size depending on which speeds you need to run the network on, or I should say, the number of ports you have and which clock frequency you want to achieve, etc. So you break up the packets. So inside hardware, of course, you can't have flexible sizes. You have to have a fixed size. It's a bus that this is going through. That is then cell by cell sent to what we call the Ingress packet processing, and that's where we have our pack language, and I'll come back to that. This determines where the packet should go and how it should look like. It has, to its help, it has some tables that's set up by software, etc. Routing tables, switching tables, etc. Once you've determined where the packet should go, you store it in the buffer memory. It's stored as cell by cell, and each cell is linked to each other so that you know that there forms a packet by linking the cells to each other. Besides storing the cell, you then send a link to the first cell where it's stored to the queue manager, and the queue manager puts that pointer basically to the first cell in its queue. And the queue is, of course, determined from your Ingress packet processing. It might be one, it might be multiple. And the beautiful thing about a shared memory switch is that even if you're multicasting, you're just writing the packet once, but you're writing into multiple queues. So it happens instantaneously. You can start to send out on multiple egress ports. So now we reach, basically when you reach the buffer memory, you have admitted the packet. It's now going to be sent out to somewhere. And you know also where it's going to be. And you have queued it on a certain queue, and there might be one or multiple queues towards the egress port. I should say one or thousands of queues, depending on where your network is or your device is situated. The scheduler then has a number of rules, you know, how often should I visit, what's the bandwidth of a certain queue, so it will select a packet for a specific port. It walks in a round-robin order between all the ports to determine where to send out the packet. Then that first cell is read out from buffer memory. The egress packet processing starts to say, it extracts a field from the head of the packet saying what did the ingress tell me to do with the packet, and what is the egress port that I'm going out on, and then it starts to transmit or modify the packet as it should be on that specific egress port, and then it can send it out. And then it comes to the parallel to serial block, where it actually breaks it up from a cell format to a smaller interface towards the Mac. And if you look at this is pretty standard for any Ethernet switch out there. There are, of course, ways you can do. There aren't that many different, you know, should say, flavors of doing this, at least as I've seen from multiple companies out there. Yeah, so now you have a background. So this is what our IP does. It's a generator that generates all of this. So let's now move into the packet processing part. So our requirement that we had when designing this was that we need to, first of all, wire speed for all packet sizes. That's something that we have to meet. In our case, we have certain customers that are low end. They want build on an FPGA because they have something else that they're doing especially on an FPGA, and then they want to have a switch or a router or something that processes packets, and then they come to us. Or on the other hand, you have terabit speeds switches, routers that might be for data centers. They might be on a NIC card. It might be anywhere basically. So we need to have that low speed to high speed, and of course you can't take the super high speed and then apply that to low speed, because then it's going to be way too large. And the complexity of the program is also so that you might have a simple L2 or a very complex edge device which has VPN, OpenFlow, SDN, etc. So all that needs to be also fitted inside this. And of course, the tables and sizes of things should also be configurable by the customer. That's, you know. So we couldn't write RTL code for each customer because that's going to take too much time. And we couldn't write RTL code that also targeted a specific architecture like an FPGA or a specific ASIC technology. We won't have a generic way. So that makes it harder for us to code it by hand. And then, continuing on this, it says that, packet processing changes continuously, which talks to why P4 is becoming more and more popular, I would say, or I should say programmability. And new standards evolve. I would say today it's the vehicle that's the TSN standard that's evolving, that's bringing lots of new features. And actually what would be interesting in the future to see if that, the P4 that we have today, can you use that to actually implement TSN networks? The problem is that I think that you can't. P4 was developed for specific solutions, such as I want to add yet another lookup, or I want to add another packet decoding layer. That's great, but what about timing things? So I'd like to see that if that's actually possible. And as I said before, each customer requirements are unique. And as we have said, the developing of packet processing pipeline is a large effort. And also writing RTL on the current lag, like VHL or Verilog or System Verilog, is just too tedious and requires timing fixes for each design. So that's not a go. Now, our observation is this: if you look at the packet processing pipeline, what does it actually do? Well, it is the incoming packet comes in as cells, as we described before, and it goes through a pipeline of steps. And each step you can do whatever you like, really. You're supposed to extract packet fields, then you extract the fields, and then you do a lookup on that, and then based on that you do modifications to the packet, etc. But it's still always moves forward. You seldom have to look at other fields than your head of the packet. You could say that, what if you want to do deep packet? Well, you want to look at the payload deep inside. Well, I haven't. Then you're probably looking for some kind of different architecture, in all honesty. So that's kind of how our view of the packet processing pipeline looks like. You can never stop the pipeline. It's always continuing onward. Because if you stop the pipeline, you will have basically a port saying that it's sending too much data. And then you're not meeting the wire speed requirement, which is the hardest requirement that we have. So what are you supposed to do then in this ingress egress? Well, as I said, the ingress part, you're supposed to extract the packet fields, do lookups. Based on the lookups, determine where you're supposed to go, record that information so that egress pipeline knows what to do with the packet, but we don't modify the packet. You might ask why. And the why is that ingress mirroring. In Ethernet, there's something called mirroring. Mirroring is supposed to say that a packet comes in, and you're supposed to be able to say that I want that packet out on a certain port, because someone there is looking at the logical analyzer saying, what is the packet that's coming in on this specific port that's destroying the network, something strange is happening. Then you're supposed to input mirroring. So you need to send out an exact copy of how the packet came in. There's also called RSPAN, where you're basically sending that packet over a network also, but that's beside the point. Anyhow, don't modify a packet. So I can't modify it, because then I would modify it on the ingress and then again on the egress. They might say, what's the problem with that? Well, modifying packet is extremely expensive. You're basically talking about big barrel shifters where you're supposed to shift data in. And doing that multiple times is very expensive. You might think that it's not, but it actually is. Okay, then as we said, we store the packet. What about an egress? The egress is supposed to extract the information from the ingress, modify the packet accordingly, and then send it out. And then again, there's something if you looked at the picture that I showed before, there's something called requeuing. If you requeue a packet, why would you do that? Well, if you're doing L3 multicast, you're supposed to modify the packet, basically route the packet multiple times, but with different VLAN headers. So on the same port can go out multiple times, the same packet data, but with different headers. So therefore, you're requeuing the packet over and over again, but changing certain fields inside it. So that's what you need to do also, or you need to be able to do. Okay, now, what about the language that we came up with? Well, we took C. You might say that's not very high level. Yeah, but compared to Verilog, it's very high level, in all honesty. So basically, we have always a main function This is the ingress main function. There's a similar one to egress. And these ports are basically input ports, that data that's coming from your switch. It's, the source port, the input cell, that's the data. Is it a header? Is it a tail? Is it express? Express is something that there's a standard that is called, doesn't matter what it's called. It's an IEEE standard that enables you to basically send higher priority packets in the middle of a lower priority packet. So you're basically terminating the lower priority, sending a high priority, and then you're continuing with low priority. So that's what's called express, 802.1.br. Anyhow, and then the source bytes, you need to know how long the packet is or how long the cell is. And then there's the output signals, like output cell, destination queue, destination bytes, etc. And then the port mask saying to which port it's going to send. And of course, packets can be dropped. So therefore, you need to tell them that this packet should be dropped also. Then there's three parts you should say in the language. First, registers. It's extremely important from the software point of view to be able to write certain things to your pipeline saying, well, I should always drop packets that has a specific Ethernet type. I should, L2 functions, L2 router tables, etc. needs to be written from the software point of view. So you need to define in your language, how are those defined? So we basically call them regs, as in registers. This example here is just a register so it's actually an array of registers. And you might say, well, that's a RAM. Yes, but we actually made the difference. So a RAM is a physical implementation of RAM, which I can only read out one time, while a register I can read out multiple times, which is true. I mean, register that is then implemented as flip-flops, and a RAM is implemented as a physical RAM. And then at the bottom here, you can see that where a usage case where I first define the registers at tag 1, it's called. Then I read it out based on some packet data, comes some data, and then I do something with it. So it's pretty simple usage. And then you might say, what's all this descriptions crap? Well, when we defined this, it was important for us to have one single source of information. So the single source of information is our source code. And from that, we then generate all the information we need. We generate C header files, we generate data sheets, we generate a certain amount of verifications components. So all that information comes from a single source, and that's our pack code. Moving on, we have 4 minutes left. The RAM by itself is pretty similar, so I'll leave that for now. And it has those if-defs. That's how you basically get features turned off and turned off, turned on and turned off. Sorry. Yeah. And this is a RAM of 256 entries of, as you see, it's just a few bits. So what is the overview then? So we have this pack code that we have built ourselves, defining lots of stuff. We have this YAML file, which basically defines which features should we turn on and how large should they be. So it's sizing. It goes into our front-end compiler. From the front-end compiler comes a data flow graph, which is basically operations and dependency between operations. I'll show a picture. And then we put that into what we call our PackOpt, which is our pipeline tool and optimizing tool, because of course, when you have this graph of independencies, you can say, well, this is used 2 times, so we can actually optimize this away. So you can do certain things on this graph and optimize that graph. And the pipeline, basically in such pipeline stages, depending on where you are and how high speed you want your pipeline to look like. So this could be a data flow graph. See, so it basically displays the operations, the logical arithmetical operations in your pipeline, and then you would then cut this pipeline in certain stages here, basically inside pipeline stages, depending on how many operations you can handle inside this, inside your timing window, basically how fast you're clocking your design. So what that gives us is we don't have to write any low-level code, as in I need to open this memory, etc. We don't have to care about the pipelining. We do get a Python simulator of this DFG graph that we can actually simulate and see that we have achieved what we're supposed to do. We have we get a C model that can use for software development that basically says this is how your switch is going to work. And then, as I said, we can automatically pipeline harder or lower depending on the implementation, if it's an ASIC, if it's an FPGA, etc. And if you see a longer memory inside this pipeline, that basically your pipeline data just flip-flop to flip-flop to flip-flop, we see that and actually says, okay, we can instantiate delay line here instead. That means that you will have actually a smaller area. And those are things that is done automatically without our without us having to, fiddle around with the code. And what could be the next steps for us? Well, you could actually build a P4 pipeline using PAC. So basically using the HLS language to build the P4. You could also take the PAC data graph and try to apply that on a P4 pipeline, if you like to. But that's things for the future. And I think that pretty much concludes my talk.
Okay. Thank you, Robert. And we have a question or comment here in the chat. Do you see the chat, or I can also read it out if you wish.
I do now.
I can read it for you if you wish. That sounds super interesting. This is a question by Gianni Antichi. That sounds super interesting. I wonder what's the cost of this high-level abstraction. I think the cost on the chip might be higher than writing plain Verilog.
Since there are ways where you wouldn't see yourself how to optimize the code, I don't know if it's always true that you are actually seeing a higher cost. I would say, okay, you can put more engineers on the problem, and you probably would have a smaller pipeline, but I wouldn't say more than 5 or 10%. So okay, so if you looked at the switch, there were two parts. We talked about HLS part and then the other parts, which is actually handwritten. Now the handwritten part, we always have to work with to achieve higher speeds, etc. when we have a new target to meet. But when the HLS is turning a wheel and say, okay, so this operation, for instance, okay, we're comparing a 128-bit number now. That's not meeting timing. Okay, so then we have to go in and say, well, okay, so let's split this operation into two, actually. So let's do two comparisons of 64 bits and then see if they're two valid. And then we've done that, and then you actually can meet higher performance again. So I would say actually it's easier for us to meet higher performance compared to doing it handwritten, just because you're working on that higher level, I would say. And a second thing is that ASIC customers, when you go down to 14.7.5, you can't access a memory in single cycle. They say, well, we want ECC on the memory and comes out, and then we're going to put it over here, so it's going to be an extra delay cycle. Yes, that's fine for us. We can say, well, this memory is going to have 5 cycles in delay. Then the pipeline will actually say, okay, so all the data that's waiting for that is going to be pipelined 5 extra cycles. So it gives you so much flexibility, I would say, when you're doing physical implementation and when you're doing just compared to handwriting this. So it is a very powerful tool. But I think that's, you could probably say 5 to 10% is wasted. But I would say in the grand scheme of things, it's not much.
Okay, thank you, Robert. I think for the sake of time, we have to move forward now. So let's take the second speaker in now. So Marco Savi is an assistant professor at the University of Milano Bicocca. In 2016, he pursued a PhD degree in information technology at Politecnico di Milano. And from March 2016 to March 2020, he worked with Fondazione Bruno Kessler in Trento, Italy, and as a researcher and expert researcher, and he's currently working on several topics related to telecommunication networks and cloud computing, including data plane programming. So, Marco, prego.
Okay, I was muted. You should. Can you hear me now?
Yes.
Okay, perfect. 1 second that I share the screen because. Okay. Do you see the screen?
Yes. Great.
So thank you very much for the introduction. Before starting, and I want to say that this is a joint work with my former colleagues, Damu Ding and Domenica Siracusa, who I want to thank. So as you may understand from the title, what we are interested in this presentation is to exploit data plane programmability to offload some monitoring and security tasks to the switch data plane. So we realized that DDoS detection is a very promising task to be offloaded. In DDoS detection, especially volumetric DDoS attacks, especially volumetric DDoS attacks, a lot of bots of compromised users flood with the traffic a few number of victims trying to disrupt their services. So with a programmable switch, it is possible to identify whether something is going wrong in the network and to detect whether a DDoS attack is occurring directly in the switch pipeline. This is not a new approach indeed. There are at least 2 approaches related to DDoS detection already implemented in P4. One is based on cardinality changed based detection, where the number of source IPs is tracked, contacting a specific destination IP, and if this number suddenly increases, we may be under DDoS attack. Another different approach is entropy based. So in this specific case, what is tracked is the destination IP's entropy over time. If this entropy strongly decreases, this means that most of the traffic is concentrated towards a few number of destinations, and this may also be a symptom of a DDoS attack. So we also focus on entropy-based DDoS detection in this specific work, but with respect to the state of the art, there is a fundamental difference. P4 DDoS, which is our strategy, does not require to store any pre-computed number, pre-computed value in TCAM or RAM memories to estimate entropy. So with our approach, TCAM is never consumed, as RAM consumption is low, let's say, while we consume a good amount of arithmetical and logical units of the hardware. Our approach just needs the P4 supported operations to work, which are shown here in the slide. So how a little bit more in detail the existing approaches works. In the existing approaches, there is a table in the TCAM or SRAM, a ternary match and action table or an exact match and action table that has some predefined rows that are used to estimate some values starting from an input value. Let's consider, for example, this number here, 111, which is 7 in base 10, and we want to estimate something, for example, the logarithm of the number, exponential function, or something related to entropy, let's say. This table is specifically designed to compute the base 2 logarithm of the input number. And how it works. Actually, what happens is that the input number is applied to a mask. The mask is this number here. Applying the mask means computing the pairwise end operation, logical end operation, and so the result is then compared with the key. If the 2 numbers are the same, the output of this operation is the number stored in the action in the output column. So in this specific case, the last row is the one that matches to this number. So the base 2 logarithm of 7 is estimated to be 2, even though we know it is closer to 3 than choose. However, if we populate with more rows, with more pre-computed value this table, we can get better estimations, of course. We completely change the approach. So in our specific case, we write the estimation algorithm directly in P4 by only using arithmetical and logical operations. This is an example of a part of the code for our logarithm estimation algorithm. And once it's compiled, then it can be used to estimate these values, logarithm, exponential, and so on, directly in the data plane. So the journey towards P4 DDoS has been pretty long. We started by building an algorithm for the estimation of logarithm in P4. Then we used it as a building block to estimate exponential function. By P4X, it's also possible using this trick to estimate divisions between numbers. Then we use this P4X as a building block to implement the query operation of the log-log algorithm. Log-log algorithm is a streaming algorithm that relies on a data structure called log-log register, which can be used to estimate the cardinality of an input stream. We are specifically interested in the cardinality of destination IP addresses in a packet stream, so how many times the same destination IP is seen in the packet stream. And so we can estimate this value exploiting P4Exp. Then we used these three building blocks to define a strategy that is called P4N entropy. N stands for normalized. So what we do here, we first estimate the entropy, not normalized, and this is shown in the previous work. Then, by also using as input the output of a P4 log-log during its query, we can estimate the normalized entropy, which is a number between 0 and 1. At this point, we can use P4N entropy as building block for P4 DDoS, which is a simple threshold-based system that allows to detect whether a potential DDoS attack is occurring or not. So here I just want to quantify a little bit the differences between our approach and the state of the art for the estimation of logarithm and exponential functions. As you can see, with our approach, we consume a good amount, we require a good amount of operations while we do not need any match and action table. While for the state-of-the-art approaches, no operation is needed, but around 2,000 match and action entries are needed to get more or less the same estimation accuracy between the two approaches. So now we focus on these two blocks here for the sake of time, of course. So I first want to explain to you how our P4N entropy strategy from a quite high level perspective. All this strategy has been implemented in P4 and in the P4 pipeline. So every time a packet comes to the switch, what we do, we extrapolate the destination IP address and we continuously update the log-log register here. Then we also update a counter and give as input this destination IP key to a sketch, which is a probabilistic data structure, compact data structure that is used to estimate the frequency of this specific destination IP, FI. So how many packets so far have been sent to destination IP in the time interval considered. So this value, as you can see from the formula of entropy, is very important because it makes a continuous change to this sum that we call the sum, okay? So we continuously update this sum for each packet using this estimated formula. The rationale behind this formula, you can see more detail in our previous work, is to try to reduce as much as possible logarithm computations because they are quite costly. So with at most one logarithm computation, we are able to estimate this sum. At the end of the time interval, then we can estimate the entropy using this other estimation. And also in this case, we try to minimize the number of logarithm and exponential function estimations. Once we have the estimated entropy, not normalized, and we have queried our P4 log register at the end of the time interval to get ndist, we can estimate the normalized entropy. So we also evaluated our strategy, and we compared it with a previous work that is called SOTA entropy, where the approach is pretty similar, but the main difference is that they use stored pre-computed values in the TCAM to estimate this product here. They also need a sketch to estimate Fi, and what we show here is how the relative error in the entropy estimation changes by varying the number of rows and number of columns of the sketch NH and NS. So we consider the two different sketches, count mean sketch and count sketch. Count mean sketch is faster than count sketch, but also less accurate. And this can be seen from these results. If we increase the NH or NS, we can see that the relative error decreases for all the strategies. But in general, using a count mean sketch leads to higher relative errors than using a count sketch. However, with a quite limited amount of memory to be allocated for this sketch, with both SOTA entropy and P4N entropy, we can get relative errors that are smaller than 3%, which is pretty acceptable, I would say. Okay, the state of the art leads to slightly better results, but as we will see later, this does not affect the DDoS detection. So, our P4 DDoS strategy is shown then in this slide. Here we estimate that we are under the DDoS attack if the normalized entropy in a specific time interval t is smaller than a defined threshold that we call the lambda norm. So at the end of the time interval, we take the output of the P4N entropy block. So we compare the normalized entropy with the threshold. If the entropy is smaller than the threshold, we assume to be under a DDoS attack. We raise a DDoS alarm to the controller, and we do not update the threshold. The threshold is dynamic, but in this case it is not updated because we want to update it only in the case of normal traffic. Instead, if we are not under DDoS attack or under potential DDoS attack, we update the threshold using this formula. EWMA is the exponentially weighted moving average. Alpha is a smoothing factor. It's very important to carefully tune this value. So you can understand that the current threshold depends also on previous entropies. And we consider here a minus epsilon, and also this epsilon is a very important parameter to tune because if it is too small, we have high false positive. If it is too high, closer to 1, we may have a lot of false negative. So we evaluated our P4 DDoS strategy. We considered the KIDA flow trace for the legitimate traffic, and we combined it with the Booter DDoS attack traces that can be found online. So we consider initially 50 seconds of normal traffic divided in 50 time intervals. Then these other 50 seconds of normal traffic from the KIDA trace are combined with the 4 Booter traces, one at a time. We also considered a final mixed trace where we assume that all 4 attacks are happening at the same time. This is quite not very realistic, but we want to see how our strategy behaves. As evaluation metrics, we consider the true positive rate, the false positive rate, and the detection accuracy. we carefully tuned, we did a lot of experiments to carefully tune the important parameters of our strategies, alpha, epsilon, NH, and NS, and we realized that with these values, we get the best possible results. So then we compared our strategy with SOTA DDoS. SOTA DDoS is a DDoS detection strategy built on top of the SOTA entropy strategy that we saw before. It was not very easy to compare our strategy with the state of the art. So what we did was to consider the best possible parameters for our strategy and to vary the sensitivity coefficient K, which is a tuning parameter for SOTA DDoS, to see how if the two strategies can have comparable performance. If K is quite small, we have high false positive rates, but also high true positive rate. While when we increase it, it behaves the opposite. What we realize is that with K equal to 3.5, the performance of our approach and the performance of SOTA DDoS are comparable, as you can see here, with slightly better performance in our approach, but let's say that we can have a comparable false positive rate, true positive rate, and detection accuracy as the state of the art. So to conclude, what I presented in this talk is a new entropy-based DDoS detection strategy that is fully implementable in P4 programmable data planes by only relying on estimation based on the limited number of the available P4 supported operations. Our approach with respect to the state of the art does not require any TCAN consumption and quite small SRAM consumption. We need to store as the state of the art the count mean sketch, the log, and the log register, and also some intermediate values during our computations, like for example sum. And our strategy avoids any communication between data and control plane, but if a DDoS attack on a potential DDoS attack is occurring. So we also compared the strategy with a state-of-the-art solution, showing that they can have very similar performance. So we can conclude that what we propose is an alternative, a valid alternative that can be adopted every time TCAM and or SRAM memory are scarce resources or want to be preserved for other tasks, like, for example, for forwarding table on other tasks, other monitoring tasks. So this concludes my presentation.
Okay, thank you, Marco.
You're welcome.
We can maybe have one quick question before moving forward. Anyone? Question?
Jari, I have a question. Salvatore. Okay. Marco, so let me understand. You used the log structure for compute the cardinality, right?
Yes.
Yeah. But usually is used when you have a very large cardinality. In your experiment, because I always say faced this in my experiment, you really need all this huge range of up to, I don't know, billions of different keys, or we are actually using a too strong structure with respect to the cardinality that is enough to detect a denial of service, let's say 1,000 or 10,000 different destinations. Is not enough in your experiment? So I'm not a clear answer.
Yeah, the question is very interesting. I mean, we decided to use the log algorithm because actually with a quite small amount of memory we were able to get satisfactory results. But yeah, I mean, in general, you may be right in the sense maybe we could have used some different approach to estimate this cardinality. However, I mean, at the beginning, you know, we wanted even to use hyperlog-log, but the query operation cannot be implemented in P4. Okay, so we use the log-log, which is a little bit less accurate. So why I'm saying so? Because maybe you're right. We may have a thought about other simpler strategies to estimate the cardinality. However, we didn't think too much about this aspect. I think with the Kaida traces, you know, the different number of destination IP addresses are, I don't know actually, but in the order of thousands for sure, but I don't know how much with these traces. I should check. But yeah, I mean, maybe you're right, but the log register does not consume much memory, so we didn't think much about this, so we just used it. You're right, anyway.
Okay, thank you. So time to move forward. So our next speaker is Dr. Chengchen Hu, and he's a principal engineer at Xilinx, and he's leading Xilinx Labs Asia Pacific, based in Singapore. His recent research topic is software hardware co-design of networked processing systems. So, Chengchen, please, the stage is yours. We cannot hear you.
Okay, Chengchen, you are muted at the moment.
Okay, so can you hear me, guys?
Yes.
Yes, now.
Okay, and can you see my screen?
A little small.
Can you see my screen? No?
It's a little small. The slide is a little small, but okay, it doesn't matter.
Oh, okay, so, okay, I'm not sure what's the cause. So can you see it clear, or let me try to share again. Is it is it okay now, or still?
It's the same. It's small, but okay. Let's go on with this one.
Okay.
Yeah, small but visible.
Okay, so yeah, sorry for that. So maybe can you give me 1 minute? Maybe let me try to fix that. So give me one minute. Okay.
Okay.
Yeah. Is it better now? Is it fixed?
I
we
think
can see only part of it.
Yeah, it's bigger, but yeah, it's cutting part of that. It's square.
Oh, sorry. So I'm so sorry about that. So how about now?
Yes, you go in slideshow, maybe. Could you go to slideshow?
And what do you see now?
Yes, but we see the PowerPoint, but can you go to the slideshow in your PowerPoint, the small icon right to on the below right? Below? Yeah, you have an icon. The next one, next to the, no, below.
Okay, sorry. So yeah,
in the bottom right corner, there's a percentage of how large the slide is. So there you can put it up to like 100%, and then you will be the whole screen. There you go.
Yes.
Now it's
Okay.
good.
So it's
Perfect.
good now, right?
Yes, perfect.
Okay. Sorry for the unexpected delay. So and thank you for your patience, and also thank you for the introduction. I'm really it's really my pleasure today to introduce our work our work on the open source the SmartNIC initiative. And as you all know, it has already been a paradigm in data centers that computing is transforming from CPU-centric to disaggregation and offloading functions. And SmartNIC plays a very important role in this transformation, and we have seen many functions moving from CPU to SmartNIC. Not only the networking functions, but also like the crypto, decrypto, codec, and so on. Quite a lot of functions. The innovation on SmartNIC will continue. We definitely believe, but we also face challenges. For example, okay, it is not so easy for us to faster prototype our ideas on SmartNIC. So in this presentation, I'd like to share and introduce our work on implementing common functions of a SmartNICs, which we call as SmartNIC shell. It is a co-work with my colleagues I listed here. And then based on this NIC shell work, I will present another work based on the NIC shell to accelerate the permissioned blockchain application. And lastly, in my presentation, I will introduce another platform which provide the open access to remote FPGA SmartNIC for the academic use. Okay, so let's start from the OpenNIC. Okay, so generally speaking, you can have all kinds of function to be customized in SmartNIC. But since it is a NIC, right, so it must have some common requirements or common functions. For example, it needs to support network ports, and it needs to have some function to exchange data between host CPU and the SmartNIC boards, right? So instead of repeat building these common functions, we would like to have this in a NIC shell, and at the same time, it would be always very good to have very good interface for you to integrate your unique user logic in a SmartNIC. So if we could have this ready, then the prototyping of a SmartNIC would be much easier and much faster. So this is the motivation, and also keep this concept in our mind. We have designed our Xilinx Labs OpenNIC, and we can see it has the hardware part and the software part. So in the hardware part, we need several subsystems to support the MAC, the DMA, the register, and so on. Also, we need a very well-defined user logic boxes in the hardware with very clear clock structure, very clear interface, and also we need to make sure there will be sufficient logic and memory resource as well for you to have your customized logic available. And in the hardware, also we have a set of utility blocks, which are usually the FIFOs, XI stream buffers. And obviously, we cannot ignore the driver to make it working as a SmartNIC device. So let's look at these parts one by one. So first, from this slide, we can see the overview of the hardware. The CMAC subsystem is to support up to 2 QSFP28 ports, And we also have the QDMA subsystem, which supports up to 4 physical functions and up to 2K queues. We also have the data bus enabled by AXI stream, and we use the AX Lite to form the control path. So you can see from the diagram on your on the right, our user logic box is in the middle. If we zoom in, we can see more details, right? And the blue boxes are CMAC subsystem, as I said, to be enabling or to connect the QSFP28 port. And we have the green boxes, which are our hardware module to enable the QDMA and be the interface between the SmartNIC and the host CPU. We also have the yellow box as the system configuration. So you may have already noticed that there are 2 black boxes, which are the user logic boxes. So in fact, okay, these 2 boxes are different. So from this slide, you can see the detailed comparison of the these 2 user blocks. In fact, they have different clock frequency and also the interface. The left one has more interface signals, but is working at a lower frequency, and the right one is in the opposite. So this design gives users more flexible choices in practice. And if you ask how user logic can be added to the OpenNIC, and here what we need to do after implementing your customized functions. So you need to implement the AXI stream interface and AX Lite interface, modify the configuration of user logic box, and then connect it to the reset system. And also, P4 generated plugins can be incorporated, but for this version, it is not ready yet. And also, okay, we have already several early users of this OpenNIC project from the research community. So who are playing with OpenNIC in integrating many interesting user logics. So here I just like to thank them for their great support and very valuable feedbacks. Yeah, so really thank these partners. And we also tested the resource utilization of the OpenNIC shell hardware on 2 boards, especially specifically they are Elvo U250 and U280. Now we don't support other boards, but in the future we expect in the community might add more board support. From this result, we can see both the logic utilization and the memory utilization are under 10%. So the rest resource and the memory and the logic should be sufficient for most of the user logic customization. So this is also a very important for people to use it. And this project also comes with a kernel driver with its structure as shown in this slide. Yeah, so it supports the kernel network stack and support eBPF. Okay, so OpenNIC implementation has been available at GitHub. So if you are interested to use it, learn more about it, or want to even contribute to it, please screenshot this slide. But I think the slides will be available later, right, on the website. And I just would like to mention, okay, sorry. So yeah, I just would like to mention, because of the license issue, right? So we have different licenses for the hardware and the software. So we split the implementation into 2 repos, and we have another repo. We call it OpenNIC repo. So under this umbrella, we have a script which can be used to check out the latest version of the hardware and the software, and there will be more documents in that repo. So it is all good for you to check the first one, and also because they are decoupled, right? So if you only want to use the hardware or software, you could also use the other 2. Okay. Okay. So the next one I'd like to talk about our blockchain machine user case, which leverages the OpenNIC shell I just mentioned. So here, okay, this user case is to accelerate Hyperledger Fabric, which is not associated with cryptocurrency. And in fact, it falls in the so-called permissioned blockchain. So for your information, so the cryptocurrency, usually we call it like unpermissioned blockchain or public blockchain. Every people can join to write and read ledger. But for permissioned blockchain or private blockchain, only the parties with the permission can read or write the ledgers. So in fact, it is the okay. So here we are working on the Hyperledger Fabric project, so which is open source under Linux Foundation, and we choose it for several reasons. Okay, its consensus is based on energy efficient raft, and it is most widely used one on the Hyperledger umbrella, and also it is adopted in a wide range of industrials. So I listed some of the companies or industrials who are using the Hyperledger for your information. So the original design is in software, but we find there is some opportunity to be accelerated through SmartNIC or through some hardware software co-designed solution. So about 2 years ago, we had a paper profiled Hyperledger Fabric, especially for the validation phase, and we found it is very promising if we split. Okay, maybe I could use a laser pen. Can you see my? Oh, it is not the laser pen. Okay, no problem. So okay, from the bottom left part, you can see the Hyperledger Fabric phase. There are 3 big steps. The first one is for the endorsement validation. You will validate the transaction, the blocks, and then the second one is to validate to verify there will be no write rate conflict and to avoid double spend. And later, the third one is to commit into the disk. So in this process, okay, we can see if we split this processing into hardware and software, we may achieve some benefit. And we did it use the OpenNIC shell. We can see the green boxes are the offloaded hardware functions, and after the implementation, we can see the result. Very good result. We can achieve about 15 times speed up through such kind of offloading or the software hardware co-design. And also, we have a plan to make it as an open source project available at the GitHub, but we are wrapping up the documents and the projects. It will be available soon, and it's under also Apache v2 license. For more information, now you can read this paper for information. And the last one, I have one slide to introduce XACC. So XACC is the Xilinx Adaptive Compute Cluster. And we have built four, in fact, we have built four XACC. We have built four XACC sites in ETH Zurich, UCLA, UIUC, and NUS. Each site is equipped with Xilinx Evo accelerator cards, and we provide remote access to use these acceleration cards. And here is the link. Okay, if you are interested, you can join this program and enjoy the remote access to the IPG card, and you can have your SmartNIC related or other IPG accelerated experiments down there. Okay, so I have several summary remarks to end my presentation. So the three projects we initiated are for speeding up the innovations of SmartNIC, or also can be generally computing acceleration with IPG. They all have a very good shape to use now, but there are still many to be enhanced. And so I hope anyone who has likely mind and who wants to use, to learn, to participate, to collaborate, very welcome. And I also list my email address here. Any comments and the discussion after this event definitely will be very welcome. Okay, so that's it. Thank you very much.
Okay, thank you, Jensen. Let's take the questions and answers through the chat, so we can move forward and catch the schedule. So let's move to the next speaker. We have next.
Sorry, there is a question from Gianni. So I don't know if you can. I can read. So Gianni asks if which are the difference between the OpenNIC project of Xilinx and the Corundum project that is, let's say, quite well known in the academic community. So I don't know if Jen wants to say something about this.
Hello. Hello.
Okay, let's take the answer also through the chat, and let's move forward. So we have next Hesam Solfagari waiting. So he received his PhD in computing and electrical engineering this year from Tampere University, where he is currently a postdoctoral research fellow, and his research interests include design of packet processing hardware with emphasis on programmability, flexibility, and high performance. So, Hesam, you're welcome.
Hi, can you hear me and see the screen?
The voice is low, but we can hear you.
Okay. Yeah, so hello everyone. I'm presenting architectural choices for the programmable data plane. Here is the agenda. So the major part is the discussion of the architectural choices. So by now, with all the presentations, we are all familiar with packet processing. We know that the two main operations are match and action. And so I will just mention this about match, that the outcome of the match could be either the address of the instruction to be executed as the action, or sometimes we already know the action, but we need to retrieve some parameters for that. And so this is the action, and the outcome of the action is either a modified header field or modification of state. And also we are familiar with these two concepts, so I can roughly say that all the components that you can see here are part of the data plane, even the tables, but the fact is that control plane is just in charge of filling in the match tables. So we need standardized interfaces for that purpose, but this presentation is about the data plane. So one of the recurring questions is why not use the general purpose processors that are quite powerful and their processing power is on the rise generation by generation. And so the reason is that for high performance packet processing, we need abundant on-chip memory. And also, as we will soon see, we need either a deep pipeline or massive multi-threading. And again, these are things that are not achievable with general purpose processors. So we need CPUs for general purpose processing and packet processing systems for packet processing, and none of them is to replace the other one, especially when high performance is the concern. So regarding the role of the architecture, so it defines the capabilities of the system, and in many ways an architecture can be compared to an algorithm. And just to give an overview of how important an architecture can be, consider a switch with 32 1 gigabit ports. So for sustaining the line rate, if you have a custom architecture, only operating frequency of 50 megahertz is sufficient. So hardware has a lot of substantial power inherently if designed right. So even at low frequencies, it can be quite powerful. And so we can see the layers in any computer system. So when designing packet processing systems, the major focus is on the microarchitecture in order to define the internals of the individual functional units and also how they are organized with respect to each other for achieving the performance goal. So when it comes to instruction set architecture, then there is not much that can be done, perhaps some bit field manipulation instructions, but other than that, the major part is on microarchitecture. So we have two main alternatives. There is like one of them is pipeline and the other one is run to completion. So in pipeline, the processing is divided into stages and the packet traverses through them. Then we have run to completion is basically a processor with a program control unit. So regarding the pipeline, on the positive side, so we see that it suits the nature of packet processing, especially when it comes to layer 2 and layer 3 processing. And it provides deterministic performance, because if you design it in a way that by the time the packet reaches the end of the pipeline, all the processing is done, then, and also if you set the speed based on the rate of packet arrival, then you have deterministic performance. You know that you can sustain the line rate and there will not be buffer overflow. And on the negative side, the negative side, one of them is that the sequence of operations is determined by the pipeline organization. So here in this figure, for instance, we have match action, a number of stages. So if for the second match table, if we need two actions preceding it, it's not possible here. So we have to just skip the second match table, and it will remain unutilized. And also not all processing can be efficiently mapped to a pipeline, something like fragmentation. So in response to these, we have the concept of flexible pipelines. So there are different variations and different levels of flexibility that can be provided. Like one of them could be adjustable action depth, or the other one can be flexibly assigning resources to the stages, but there's always a limit to flexibility because it can become very costly. Technically, it's possible to achieve very high flexibility, but the cost is usually too much. So there are two important design questions that must be answered. How much flexibility is really needed and how much flexibility can be provided given the area, speed, and power constraints. And now coming to the run to completion. So obviously it's more flexible because it's a processor, and as such it is not limited in the sequence of operations. You can have a match instruction followed by any number of action instructions. And on the negative side, providing deterministic performance guarantees is difficult. We will soon see why. And also we need to replicate the memories per core, whereas in a pipeline you divide them across the stages. So just imagine this very generic run to completion processor. We have two classes of instructions, match and action. So you can see that the dependent action instruction cannot be overlapped with the match instruction. So these cycles are wasted. So in order to enhance its performance, we can either have a large number of baseline cores and just assign an incoming packet to a free core, or we can speculatively execute all those possible actions as the match instruction is being executed. But this is also costly because there can be many combinations of possible outcome. The two solutions that are in use are fine-grained multithreading and simultaneous multithreading. So this is fine-grained multithreading. So we have one thread per packet, and at each cycle there is a switch to the next thread, and which is in turn in charge of another packet. And so those cycles that would have been wasted are now, during those cycles, the processor is busy and it doesn't sit idle. And so by the time it switches back to the same thread, then those cycles have passed. Simultaneous multithreading goes even one step further. So we know that simultaneous multithreaded processor, or SMT, means superscalar with multithreading capability. And superscalar itself means multiple instances of functional units. So let's say that we have this kind of thread. And so M's represent matches and A's represent actions. And this is the conceptual pipeline. We don't want to make a pipeline, but rather we want to achieve behavior similar to one we get from a pipeline. So in fact, if we do the thread scheduling correctly, in fact, we can get identical behavior from the SMT processor. So for instance, at this point in time, we see that we have 4 match instructions and 4 action instructions all running in parallel. And this is identical to behavior of a pipeline. So we know in a pipeline, once it is filled, then all those stages are running in parallel on different inputs. And input here is basically the packet. Then another thread, and they are another like pair of threads. They are very similar, except that the second one has 2 action instructions after the first match. So here at this point in time, T6, they both try to access M1, which is one of the tables, but it is stalled because there is a resource conflict. And the way to solve this is that different threads must be written in such a way that they have same pattern of access to shared resources. So in fact, the threads need not be identical, rather the access pattern to shared resources must be same. And when doing so, even with SMT processor, we can achieve deterministic performance. So the behavior becomes identical to pipeline. So in fact, we can, with SMT processor, although subject to some limits, we can make any pipeline. The key here is just keeping the thread scheduler very simple, and this is possible by writing the code in the manner that I just referred to. And also, the functional units need some wrapping logic around them so that different threads can be assigned to them. So in conclusion, so we know that software-defined networking has software at its heart, but in fact, this has provided new opportunity for flexible hardware. And providing flexibility can be costly, but we need careful analysis for that. And finally, if we try to solve all the problems at architectural level, it can be costly. So in these cases, software can help us avoid very complex hardwares. So thank you for your attention.
Okay, thank you, Hesam. And we have time for some quick questions. So do we have any volunteers to start asking questions? While waiting for the others to warm up, I can maybe ask, is there any difference in the complexity between these two approaches, run to completion and pipeline?
Well, I would say like with the processor, it's even simpler, because with pipeline, especially if it's a very deep pipeline, let's say like 128 stages, and if you have a lot of resources, then and you want to assign flexibly to them, then it becomes very costly. But the fact is that the major problem is again the same, like having SMT processor and trying to making it very flexible. The basic problem is in fact the same.
So actually, so I implemented packet processing pipelines, both using a micro engines, which basically is CPUs, but they weren't programmable, but they were doing a fixed show, and then this as a pipeline. And my finding was that the added complexity of buses towards these micro engines, the buses towards the common resources, the reordering as you are finished with the packet actually tremendously makes it more complex design compared to a pipeline. So the pipeline kind of won out in the end. At least I've done it so far. So that's why I don't go that path anymore. And if you look at NPUs from the early 2020s, or I should 2000s area, then you'll find that lots of people wanted to go here in this, let's just duplicate 1,000 CPUs and then that should be enough. But it turned out the performance you can get for that is pretty low, extremely low, I would say. Yeah, and I think one thing that's overlooked, and it's really hard to understand, and that is the physical implementation when it comes to these buses. It sounds simple, in software they're nothing, in Verilog they're nothing, but in reality they're loads, right? You're running these 1,000 bits buses all over the place, and that tends to be expensive. Yeah, sorry, that's just a few comments.
Yeah, thank you.
In a way, I think this also answered the question in the chat. So in terms of performance, the pipeline will eventually win. But okay, it's time to have a break.
May I ask just one question, Jari? Question to Robert Vikander. It may be a very a naive question, but when you started your presentation, you displayed the general architecture of a router, and you mentioned the shared memory. Does it mean that architectures based on switching matrices are not used anymore, or they are still alive?
No, I would say they're not used. ATM switches used to have this shared crossbars, etc. But today, crossbars are made out of actually shared memory switches. So they're not used, I would say. Okay. Even, yeah. So they become too complex when you're scaling number of ports, right? As many have described, even Nick McNeon's PhD studies, right? When he has that tiny Terra, I assume you read that. That centralized scheduler becomes fairly complex to build, actually. So, yeah.
Thank you.
Thank you.
Okay, good, interesting. Now it's time for the break, I believe, and we continue 20 to 4.
Yes, exactly.
European time. Yes.
We are on time. Okay. Have a nice coffee.
Yeah. See you soon.
See you soon.